This is part 2 of the spring final exam review for Algebra 2. So part 2 has a lot to do with factoring. And first thing we should probably do is go over the 6 types of factoring that you'll see for this final and in this class. So the first type is the most important, GCF, or greatest common factor. That's when everything in the polynomial divides by the same number or letter, and so we factor it out. The second type is trinomial. That's the add and multiply method. Number 3 is kind of a cousin of trinomial. That's the rainbow method. That's kind of like trinomial, but something is in front of x squared. The fourth one is difference of perfect squares. And the tip-off for difference of perfect squares, you'll see examples of this, is two perfect squares and a minus sign. If you don't have two perfect squares and a minus sign, you can't do difference of perfect squares. Number 5, grouping. And the tip-off for grouping is 4 terms. And the last one is perfect cubes. And we can use perfect cubes when we have 2 perfect cubes. So that list is the 6 types of factoring. If you don't know those, we will review all types of them in the next couple problems, but get used to being able to not only know how to do all of them, but identifying each type also. So number 1, 8x to the third minus 64. We should notice that we have a GCF of 8. How do we know there's a GCF of 8? Both of these guys will cleanly divide by 8. So what we'll do is we are going to pull that 8 out. And then we'll divide both of our terms by 8. We get x to the third minus 8. And what GCF means is it's like distribution in reverse. If I were to distribute this 8 out, I would get right back to my original problem. That's how I know that I did my GCF right. A little thing about all these problems, there is more than one type of factoring in each problem here. So this piece right here is an example of difference of perfect cubes. We know it's a perfect cube when we could take the cube root of it, obviously, the cube root of 8, but also when for x, the exponent is 3. That's how we know to use perfect cubes. What we're going to do is we're going to take the cube root of this first guy, we're going to call him a. The cube root of x to the third, the cube root of x to the third, the cube root and the third cancel out, is x. Then the cube root of 8, your calculator could help you out, but it's 2. And so for this, you will get this formula on the test, but obviously you'll need to know when to use it. The formula for these is a minus b, a squared plus ab plus b squared. So I have my original GCF of 8. A minus b, we sub in what we got, so x minus 2. A squared is x squared, plus a times b, x times 2 is 2x, plus b squared is 4. And so that is your final answer for problem number 1. Problem number 2, just as always, everything we do in this class, look for the greatest common factor first. Notice there's an x in all 3 of these. So I could factor out an x. So I'll factor that x out, and that leaves you with x squared plus 9x plus 14. Can this factor further? Of course it can. That piece right there, what type of factoring is that? That would be trinomial. Trinomial is where we want to add to the middle number and multiply to the last number. What two numbers do that? In this case, it's 7 and 2, so we get x plus 7, x plus 2. 7 plus 2 is 9, 7 times 2 is 14. And then we have our original GCF out front. And that's how you do number 2. Number 3, again, we look for that GCF first. In this case, they both have x squared. So we'll factor out that x squared. That leaves you with 9x squared minus 16. Now we should recognize that in this piece right here, we could factor it further by using difference of perfect squares. The square root of 9x squared is 3x. The square root of 16 is 4. So here's how we factor difference of perfect squares. We have our square roots, 3x and 4. We're going to put a plus sign between them and a minus sign. Put your original GCF out front, and you have your final answer. So make sure you know your perfect squares on this test, and really your perfect cubes too. Your perfect squares are, for example, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. These are the types of numbers you're looking for to use difference of perfect squares. Notice we had 9 and 16 for this one. And make sure you know that for cubes too, like we had for number 1. We'll get into that again in just a minute. So number 4, we have x to the 4th minus 81. First, we always look for that GCF. In this case, we don't have one, so we're going to jump right into another type of factoring. What can we tell is this type of factoring? It is another difference of perfect squares. X to the 4th, if the exponent can divide by 2, it's a perfect square. 81 we know is a perfect square because 9 squared is 81. So we take our square roots. Square root of x to the 4th is x squared. Square root of 81 is 9. Put a plus sign and a minus sign. Now we could be done here, but that would be entirely too easy. So we are going to factor this one further. Why the second one and not the first one? Because what is that first thing I said about the difference of perfect squares? 2 perfect squares and the minus sign. We need that minus sign. This one has a plus sign, so that does not factor further. X squared minus 9, we take the square roots, which is x and 3. Put the plus sign between them and the minus sign between them. And that's your final answer. So you need to know all types of factoring, when to use that, and when you can continue to factor and when you're done. You need to be able to factor until there's absolutely nothing left to factor. Number 5, again, look for that GCF. In this case, it is x. They both have x, so we'll factor the x out. I'm left with 27, x to the 3rd, plus 125. I apologize if the screen just jumped for a second. So next we're going to figure out what else we could factor. What do we notice right here? 27 x to the 3rd and 125 are both perfect cubes. How do we know that? Let's list our perfect cubes. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. So for perfect cubes, these are the types of numbers we're looking for. We see 27 and 125 right here. So what we're going to do is, just like number 1, we're going to take the cube roots. The cube root of 27x to the 3rd is 3x. You could do the cube root of 27 part in the calculator, But you can't do the cube root of x cubed part, so make sure you don't forget that. A common mistake on that test was people just giving me 3 there instead of 3x. Cube root of 125 is 5. So after we bring down our GCF, the formula now for this one, because there's a plus sign, number one had a minus sign. When there's a plus sign, your formula is a plus b, a squared, minus ab plus b squared. That is your formula for when there's a plus sign. So a plus b, 3x plus 5. A squared is, remember when we square, it's something times itself. So 3x times 3x is 9x squared. A lot of people will tell me a squared is 3x squared. That's not true. You need to multiply the whole thing times itself. So then we get minus a times b, which is 15x, plus b squared, which is 25. And that's your final answer. Number 4, we have, number 6. Again, look for the GCF. Notice we could factor out a 2x. A 2x squared from all 3 of those terms. That leaves you with 2x squared minus 7x minus 15. Now this right here, this piece, this trinomial, is an example of a rainbow method. How do I know it's rainbow method? It looks like a trinomial that we would add and multiply. The only difference is we have this 2 out front in front of x squared. That's going to make this problem a bit more challenging. So here's how we do that. Step 1 is this is why we call it the rainbow method. We're going to rainbow that 2 over to the back and multiply it. So that's going to give me x squared minus 7x minus 30. Then we are going to factor it like any other trinomial, adding to -7 and multiplying to -30. In this case, those numbers are -10 and +3. That adds to -7, multiplies to -30. Then we have one more step when we do the rainbow method. This 2 that we rainbowed over, now we have to take it back out. So here's how we do that. We're going to take it out by dividing both of these by 2. That'll give us x minus 5 because 10 divided by 2 is 5. Now 3 divided by 2 does not work. That'll give us a decimal. We don't like decimals. So instead what we're going to do is we're going to take this 2 and push it up in front of x. Bring down your original GCF. And this right here is your final answer. Nothing else can factor. I want you to make sure you got this down because this is one that I will have to erase in a minute for the sake of making room to do number 8. But first, let's do number 7. Step 1, as per usual, greatest common factor. Is there one? Yes, there is. They all divide by 2. So I'm going to factor that 2 out. And then what did we say right in the beginning? 4 terms is a sign that we need to use grouping. Grouping is when we have 4 terms. Now to do grouping, what we're going to do is we're going to take the greatest common factor of 2 terms at a time. So the greatest common factor of those 2 terms is x squared, and that's going to leave me with x minus 6. And then the second 2, negative 17x plus 102. Notice that these signs here are opposite of these signs here. When that happens, if those signs are opposite, that means we need to factor out a negative so that those signs change. In this case, the GCF is 17. So I'll factor out a negative 17 and I'm left with x minus 6. Make sure you know why we factored out that negative. That's going to be big. Because otherwise we would have had negative x plus 6 right here. We don't want negative x plus 6. We want it to match exactly. And because it matches exactly, what we can then do is take these two pieces and make its own set of parentheses. So we get x squared minus 17, and then our match. Bring down your original GCF, and right here you have your final answer. None of that will factor further. X squared minus 7 could factor further. It looks like it's a difference of perfect squares, but 17 is not a perfect square, so that will not factor further. This would be a good time to pause the video and make sure you know what's happening in all of these problems. So I'm about to erase these to give myself more room and give myself number 8. Give myself room to do number 8. So again, if you need to pause it, feel free. Number 8. Again, step 1, always, always, always GCF. In this case, we could factor out an x. All of those terms have an x in it. Four terms. Ask yourself, what type of factoring do we use? We use grouping. So when we use grouping, again, we take the first two terms at a time, and we're going to find its GCF. In this case, the GCF is x squared, and that leaves you with x plus 3. Then we look at these two, find its GCF. We notice it's negative 4. We'll factor that negative 4 out, and that leaves you with, again, x plus 3. Remember why we factored that negative out? Otherwise, that x plus 3 would, right here, would have the wrong signs. So we had to factor that negative out. And so then we group it together. This piece and this piece creates its own set of parentheses. So we get x squared minus 4, x plus 3, and bring down your original GCF. So in the last problem, at this point, we were done. At number 7, we were done. However, in number 8, we have more that we could factor. That x squared minus 4, two perfect squares and a minus sign. So we need to use difference of perfect squares. So for that, we'll take the square roots. Square root of x squared is x. Square root of 4 is 2. Plus sign. Minus sign. And then bring the rest of it down. And this is ultimately your final answer. That's 3 different types of factoring in one problem. Be ready to have to do that much. These problems can get long. Number 9, once again, grouping because 4 terms. First, we look for the GCF. We notice there is no GCF. So we'll go straight into grouping. Right here, for grouping, the GCF there is x to the third. And I'm left with x plus, and if I took out that whole x to the third piece, I took that whole piece out, I'm left with 1. And here's what else I notice. Inside the parentheses here, already matches my next 2 terms. So I'm going to put parentheses around it right away. And let me move that over just a little bit. If it already matches, you could already put parentheses around it. And we know that when there is no number in front, we assume it to be 1. So that way when we group it together, we get x to the third plus 1 and x plus 1. Now, it looks like we could be done. However, in this piece right here, we have 2 perfect cubes. X to the third is a perfect cube, and 1's a perfect cube. 1's also a perfect square, so 1 could be a perfect anything. So we need to factor that piece out. Again, the formula for 2 perfect cubes with a plus sign is a plus b, a squared minus ab plus b squared. Like I said, you will get that on the tests. So first we find a and b. We do that by taking the cube roots. Cube root of x to the third is x. Cube root of 1 is 1. So there's your a, there's your b. So when we plug it in, we get x plus 1. Then x squared, minus x times 1, or just x, plus b squared, so 1 squared is 1. And then bring down the other piece of parentheses that you haven't used yet. And so that is our fully factored form. There's nothing wrong with writing it like this. However, on a multiple choice test, this is how you may see it. Notice there are two x plus 1s when we're multiplying. You may see it as x plus 1 squared because of those two. Number 10, we have 2x to the third plus 54. Once again, greatest common factor. We factor out the 2, and we're left with x to the third plus 27. And then can we factor more? This piece right here. Take a second to think about what type of factoring it is. It's sum of perfect cubes. How do we know it's perfect cubes? X to the third is a perfect cube. 27 is a perfect cube. It's 3 cubed. So cube root of x to the third is x. That's your A. Cube root of 27 is 3. That's your B. So when we plug it into the formula, we'll get x plus 3, x squared minus 3x plus 9, and then bring down your original GCF. And there is your final answer. Number 11, just like the other ones, so we'll look for GCF first. X to the third plus 64, there is no GCF. So we're going to see what other type of factoring we could use. X to the third and 64, those are both perfect cubes. So I still have that formula up there for two perfect cubes and a plus sign. So the cube root of x to the third is x. The cube root of 64 is 4. That's our A, that's our B. So we'll get x plus 4. I'll separate that so that we don't mix those up. Then x squared minus x times 4, which is 4x, plus 4 squared, which is 16. And that's the final answer for that one. So that is a full review on factoring, a bunch of different types of problems in order to figure out, and a bunch of different types of factoring. Again, the problem I think we're running into is not necessarily the factoring, but recognizing what type of factoring to use when, and when are we done. So make sure you look at these problems and try to study that piece. Let's go to the back half of this page. 12, 13, 14, it says factor completely and find the zeros. Another way to say find the zeros is solve. So number 12, even though it says factor completely, it's already factored into 4 separate parts. So here's what we'll do. If it's already factored, we're going to take each factored piece, set it equal to 0. So here we'll divide the negative 5 away. X equals 0. X equals negative 3. X equals 4. X equals negative 8. So that's kind of a precursor to number 13 and 14. Number 12 is already factored out. When it's already factored out, you just need to set the factors equal to 0 and solve. So pause this if you need, but I'm going to erase this to give me room to work on 13. Number 13, first off, as always when we're factoring, look for that GCF. In this case, Every single one of those guys divides by 2. So we'll factor out the 2. We're left with 5x squared plus 33x plus 18 equals 0. Can we factor it further? That middle piece, right, that big piece right there, that is a trinomial with something in front. So that tells us it's the rainbow method. So what we need to do is, I'll just bring that piece over here so to give a little bit more room. We need to rainbow that 5 over to the 18, which will give us 90. So we get x squared plus 33x plus 90. Then we factor it just like any other trinomial to add and multiply. We'll get x plus 30, x plus 3. The last step, again, just like before with rainbow method, if we've rainbowed that 5 over, we need to divide by 5 on both sides. So that'll give us 30 divided by 5 is 6, so x plus 6. 3 does not divide by 5, so that needs to push up. 5x plus 3. That's how that piece factors. So I'm left with 2x plus 6 and 5x plus 3. Now, I'll clean that up for you. So that's as far as we could get factoring it, but to solve it, just like the last one, we're going to take our factored pieces and set them equal to 0. Now here's a little tip. You only need to set the pieces equal to 0 if it has an x. So this 2, for example, we factored it out, but it does not have an x. If it does not have an x, we don't need to set it equal to 0. So we'll do x plus 6 equals 0, 5x plus 3 equals 0. And so minus 6 minus 6. I'll put the answers up over here for a second. X equals negative 6. Then this one we'll do minus 3, 5x equals negative 3. Divided by 5, divided by 5. X equals negative 3/5. And that's how you do number 13. I know it took up a lot more room than we have on the page. If you need to put this on a separate piece of paper so you can see all of it, obviously I need to write a little bit bigger than you need to on your piece of paper. But again, I'm going to need to erase this to give myself room to work on number 14. So if you need to pause it to copy it down, feel free to do so. Number 14, we have x squared minus 3x minus 40. That is just a very simple trinomial. There is no GCF, and x squared is all by itself, and there's 3 terms, so trinomial. What adds to negative 3 multiplies to negative 40? We get x minus 8, x plus 5 equals 0. That's factored as far as we can. Next thing we need to do is solve it. We do that by setting our factors equal to 0. We'll get x equals 8 and x equals negative 5. On this first one, we did plus 8 on both sides. This second one, we did minus 5 on both sides. So that's, if I ask you to factor, it's just like the front page of this review. If I ask you to solve, that's when you need to set your factors equal to 0. So number 15 through 19, we're switching gears a little bit. This is no longer factoring. This is direct and inverse variation. So direct and inverse variation, what that means is if I have 2 variables and they're both going the same direction, so as one goes up, the other also goes up, that is called a direct variation. So that's either both variables going up or both variables going down. For inverse variation, this is when one variable goes up, the other variable goes down. Number 15, given the table of data, determine whether x and y vary directly or inversely. Then find the constant of variation and find y when x is 8. Constant of variation is the formal term for this a right here. That's what the constant of variation is. So first we're going to look at this table. X, it's going from 1 to 3 to 6, so that's going up. Y is going 5 to 15 to 30. That's also going up. So that's an example of direct variation. Now the constant of variation, to figure it out, a equals y over x. We're going to pick any x and y here as long as they're paired up. So we're not going to want to do pair up 5 and 3 because they don't come as a pair. So don't do that. However, we could do 1 and 5, 3 and 15, 6 and 30. And look at the formula. It's y divided by x. So let's do this one right here. 5 divided by 1 is 5, meaning a is 5. And then the word problem, find the constant of variation. Find y when x is 8. So what I'm going to do is I'm going to set up this same formula that I just used to find a, but now we don't know y. We do know a is 5, and x is now 8. So how do we solve for y? We multiply the 5 and 8. We get y equals 40. So for these direct and inverse problems, we will have to use our formula twice, once to find a, once to find the new answer. Number 16 is a word problem. The cost per student C is needed for the class trip that varies inversely as the number of students going on the trip, and C equals 7 when S equals 56. How much would it cost per student if 49 students go on the class trip? So it says right here, varies inversely. We are using that formula. So in order to do that, we will set it up. Notice it says, how much would the cost be? When it says how much, when it's asking what variable, when it's asking how much, what is, when they're talking about a specific variable, that means that variable is going to be y. The other variable, in this case is the number of students, is going to be x. So that's the information we're going to use to figure out the inverse variation. So we have a given value right here. We have 7 equals a over 56. So when we multiply, we know that a, we multiply these together, 7 and 56, we get a equals 392. Now we're going to plug this back in the formula with our new information. We'll get y equals 392 divided by 49. And ultimately that's going to mean our new y is 8. And that's your final answer. So jumping to number 17, we have varies directly. So we use that direct formula right here. A equals y over x. A equals y over x. So z varies directly as x. Z is 30, x is 8. Find z. So it's saying find z. Whatever it's telling you to find, that's your y variable. We're going to plug in everything else. So z is 30, x is 8, meaning a is 3.75. That is our a. So we set it up again. Now we know that a is 3.75 equals y over 4. So we multiply times 4 on both sides to get rid of that. Y equals 15. That's our final answer there. Number 18, y varies inversely. So when it varies inversely, we have that formula y equals a over x. So So when y is 23, x is 4. We'll multiply by 4 on both sides to get a by itself. We'll get 92, so a equals 92. Go back to your formula. Now you know a is 92, and x is... I apologize, we need to start this problem over because I messed it up. So please disregard the last 30, 45 seconds of this video. We get y, it varies inversely, so it is y equals a over x. Y is 23. I apologize, x is 8. It's that piece right there. So we'll get multiply by 8 on both sides to get rid of that. We'll get a equals 184. Now in order to do, now we'll take that a, put it back in our formula. We'll get 184 over our new x, which is 4, and that's our new y. Y is 46. And that's your final answer for that one. Number 19, the last problem of this piece of the review, the number of pencils sold varies directly as the cost. If 5 pencils cost 45 cents, find the cost of 7 pencils. Find the cost. That means cost is y, pencils is x. So direct variation again is a equals y over x. So we'll plug in this first scenario, 5 pencils, 45 cents. So 45 cents, 5 pencils. And that's our a. So in this case, a is 0.09. Plug it back to the formula. We know now that a is 0.09. Trying to find y when there's 7 pencils. Times 7 on both sides in order to get rid of that 7 underneath the y. We get y equals 0.63, and that is your final answer there. So rewatch this review if you need more help on factoring or direct and inverse variation. Factoring is going to make up a lot of the final, so make sure you know what you're doing here. Otherwise, stay tuned for part 3 of the review that's coming shortly, as well as part 4 and part 5.